here. Probably, but I don't know. Okay, so let me pull this up. All right. So can everybody see the slides? Ooh, my connection. All right. Can everybody see the slides? Just making sure. Okay, good. All right. So today is going to be a really cool day because what we're going to do is take all of the pieces of the stuff that we've been working on for the past few lectures and really sort of put it together. What we've been doing, and really this is what we've been doing since the beginning of the semester, is we've been working on the various pieces and components of our first module, which is tension members. And today is the day that we finally start putting everything together and doing some full-blown steel design. Now we start with what we call steel analysis, or steel, analyzing a member. And what I mean by that is we have a member, we have a series of loads on it, we have it, we know everything about it, we know its connection layout, what member it is, and so we're assessing whether or not it performs adequately or not. And so that's what we mean by analysis. The next thing that we'll do is, okay, we have loads, but we don't know what the member looks like. How do we select a member to safely resist those loads? And that's steel design. So so we're getting there. We're getting there. Okay. Oh, one other thing, just on quick announcements. I went ahead and posted the solution to homework 2.2. It's currently being graded. I think it'll be finished today, but the solution's up for anybody interested. Okay. So like I said, today we're going to put together the pieces. Let's talk about the pieces. Okay. So remember, our fundamental expression is the LRFD expression for a limit state, and we deal in factored loads and factored resistances. So on the load side, we take all of our individual components, our dead load, our live load, etc. We then factor those to obtain a factored load, a PU, if you will, or an RU or MU, just an ultimate load that's been factored according to the various levels of uncertainty. And then on the resistance side of things, we take our nominal resistance, which we compute based on what mechanics dictate, what the specification states, etc. We adjust it by an appropriate resistance factor, and we end up with a factored resistance. And at the end of the day, if the factored resistance is larger than the factored loads, then the structure or the element is safe. Our load combos, we've already had experience with those, so we just take our various components and plug them into these load combos, and whichever one is the maximum result, that's the one we utilize for PU or MU or VU for our factored load. Our example today is only going to have dead load and live load, so we'll probably end up just using load combo 2, and that's it. Like I said, the first two are very, very common, and by observation, if all you have is dead load and live load, you can pretty much, for the most part, use load combo 2, and you'll be fine. Now, on the resistance side of things, we have two limit states that we're assessing, so we're going to have two different PPN values that we're going to compute. We're going to have our gross section yielding PPN and our net section fracture PPN. And for gross section yielding, our phi is 0.9, and the resistance is Fy times the gross area. And for net section fracture, our resistance factor is 0.75, and the nominal resistance is Fu times the net area times our shear lag factor. Now, later on, we're going to add another limit state. This will be a couple, maybe a week and a half later, called block shear. And block shear is its own unique animal. We'll deal with that later, but it's a connection-related phenomenon that can happen with tension members. You're basically sort of ripping a chunk out of the section, but that's later on down the line. If we go to that expression, we're going to need Fy and Fu values for our grades of steel. So today we are using this table. So based on the grade of steel that we're looking at, we are going to need the Fy and the Fu value, the yield stress and the tensile stress. Remember that whenever there's a range, you always use the lower value because that's the one that's most conservative. In terms of net area, we pretty much defined our complete expression for the net area. We take the gross area, we subtract all of the bolt holes, so that's the diameter times the thickness, and the diameter that we use is an effective hole diameter. It's the diameter of the bolt plus 1/8 of an inch, and then we add any stagger factors that are needed. So that would be S² over 4G times the thickness. And all that's for bolted connections, and for welded connections, specifically ones where we're not removing any plates or removing any material, the net area just equals the gross area, so it's pretty easy. And then the shear lag factors, we find those in Chapter D of the spec. That's that table that we looked at last time, and that you all had a homework assignment on that was due today. You know, we just go through the various cases in the manual and just you know, apply all the ones that apply. Multiple cases can apply to a given connection. We are going to see that today with the example that we do. Again, this is probably worth bookkeeping. All right. Any questions before we dig right into a full-blown example? I'm sort of excited for today because we actually get to tie together everything that we've been working on. Let me pull up the chat here on this computer. All right, let's do it to it. Okay, so we have a tension member. It's a W8 by 24, and it's 40 foot long. It's made of A992 steel, and we're going to use it as a tension member. So we basically have an I-beam, you know, kind of looks like this, and we're taking that I-beam, and we're yanking it. We're pulling it in tension. We're using 3/4 inch diameter bolts, and we're subjecting this member to a dead load of 80 kips and a live load of 90 kips. We want to know whether or not the connection can the member can safely resist these loads, and we also want to know whether or not it meets recommended slenderness limitations. So for slenderness, we're going to need the L over R. We know how long it is. We need to know the radius of gyration that applies as well. We know it's A992 steel, so we know the material. We know we're going to need the FY and the FU, and that tells us what we need. We also, if you look at the schematics below, we pretty much know everything we need to know about the connection in order to assess the net area, the connection length, all of that stuff. Now, before I jump into this, one thing I will remind you, if you remember, this is a special case for the shear lag factor. We use the equivalent WT. We didn't use this during our last lecture, but if you remember, I said this is a weird one, and we're going to deal with this today. So that's going to probably be, I want to say the only new part. That's going to be the new part. Everything else you should probably be able to do pretty quickly. So with that, let's just get right into it. Let me open up my OneNote. I don't know what happened there. I sort of vanished. I'm going to share my screen here in a second. Bear with me. Bear with me. Come on. There we go. I think that's a little better. Okay. All right. Let me share my screen here. Okay. All right. So in order to do this problem, is the audio still coming through clearly? I'll assume it is. If it's not, let me know. In order to do this problem, we're going to need some properties. Okay. So I'm going to need you all to have your manuals ready. I'm going to ask for some data, and I'm going to need you to report it to me. Okay. So the first thing that we're going to need is some properties about the steel. Okay. So let's handle that part first. So for A992 steel, we're going to need the FY. We're going to need the FY and the FU value. So somebody in the chat, tell me what those are. All right, so FY is 50. Somebody else tell me what the FU is going to be. Somebody besides Trevor. I'm getting some slow responses here. Is everybody able to find this? Or is it my audio?
If I'm reading this right, 65.
That is correct. So keep in mind, I'm getting that from table 2-4 on page 2-48. Okay. So again, this is one of those sections that you'll want to place a bookmark or a tab in your manual because we are going to use this pretty regularly. And if you're looking at this table, A992 steel is it's pretty much near the bottom. All right. Is there anybody that isn't able to find that? Don't hesitate to tell me, yes, I want to make sure that you can. All right. I'm going to assume that everybody's good. Again, don't hesitate if you got any questions. You know, I'm in here in an office by myself, and I'm just sitting here looking at a chat. So if there's anything that's confusing you, let me know, and I can address it. Okay. Now, we are dealing with a W8 by 24. Okay. So we're going to need some properties for a W8 by 24. Okay. And this is going to be in table 1-1. Okay. Now, just to make sure that everybody's on the same page, this is what I'm going to do. Okay. I'm going to ask for quite a few parameters. Okay. I'm not going to ask for just one. I'm going to ask for a bunch. And in a roundabout way, we're going to use all of them, but I want different responses from different folks. I don't want the same person to give me 6 different properties. I want 6 different people to give me an answer because I want to make sure that everybody can find this. Okay, so let's start. I want AG. So here's the parameters that we're going to need. We're going to need AG. We're going to need the depth. We're going to need the flange thickness. We're going to need the flange width. We're also going to need RX and RY. So let's start off with AG. All right. Hold on. We'll take it one step at a time. So AG, we've got 7.08. It is, now just to be clear, it's not 7.08. It's 7.08 inches squared. It's the area. So make sure whenever you're looking this up that you incorporate the units. Now, somebody else give me the depth. I saw Ben Romans and Caleb Wise. Okay, so David Ball's got a depth of 7.93. That's what I like to see. There we go. All right, the flange thickness. We got Gordon Blizzard. Okay, hold on. Mr. Blizzard told me that RX is 3.42 inches. Okay, there we go. Somebody else give me, let's do the flange thickness. Anybody got a flange thickness for me? All right, 0.4. That's correct. What about the flange width? Somebody else. No, you're fine. You're fine. I'll remember that, though. I'm just kidding. Somebody else. I'll call on folks if I have to. All right, Mr. Smirchesky, that's the flange width, right? Is that, wait, 5.2. What is the 5? Hold on. What is the 5.25? I think you're looking at the wrong section. Yeah, I think the 5.25 is for the W8 by 18 for the flange. Yeah, I got what Trevor got is 6.5 for the flange width. Sorry. No worries, no worries. And then finally, the RY value. Yeah, I'm telling you, having a little like just like piece of paper to put in the manual as like a little bookmark or a little straight edge, it is worth its weight in gold. Okay, so 1.61 inches. Okay. All right. Okay, so all those values are correct, and I want to mention a couple of things that that you'll observe. We are going to use indirectly every one of these values, but I actually want to make an observation about RX and RY. The RX value is bigger, right? RX is bigger than RY. And I challenge you to find a W section where that is not the case, and you're not going to find one. Every single W section, the RX is always bigger, every time, okay? In fact, it goes to the way that a W section is proportioned. We're talking about an I-beam or an I-shaped cross-section, and they are stronger. They have more flexural stiffness in one direction than they do in another. That's why they're shaped like an I shape. Basically what Zach said. So for every W section, RX is bigger. So you might hear me use the terms strong axis and weak axis. So whenever I say the strong axis, I'm talking about the X axis, and for the weak axis, I'm talking about the Y axis. And when we do our slenderness check, we're just going to use RY, but I wanted for you to look up both to see that RY is smaller, and it will in fact always be smaller for W shapes. Sometimes it's not smaller for other cross sections, but for W shapes, always the smallest. Okay, before we jump forward, I'm just going to go ahead and handle this part real quick. 3/4 inch diameter bolts. So 3/4 inch diameter bolts. So if we look at the bolts, the bolt diameter is 3/4 of an inch. So therefore, what is the effective hole diameter? Boom, there we go. See, the actual tension member stuff's going real quick because now we've handled all the pieces. This stuff is we're just rocking and rolling with it. Okay, now let's see what we can do here. Okay, so, all right. Now, we have two limit states. Now, we have the limit state of gross section yielding and net section fracture. Okay, what's the formula for gross section yielding? Somebody in the chat, tell me, what's the formula for gross section yielding? So for gross section yielding, we're going to compute a phi PN, and it equals something. All right, hold on. What? What'd that say? Oh, PK, what? I'm missing something. Yeah, so there are two limit states, if you remember, gross section yielding and net section fracture. Let's take the gross section yielding first. How do I compute the resistance? We haven't used this formula yet, but it's in our slides. Anybody have an answer for me?
One moment here. So this is not tensile yielding. Okay.
Yes. Well, wait. I think we might be making this a little more complicated than it needs to be. Okay, so if we go to, let me stop share.
Yeah.
There we go.
That's it. Yeah.
Not,
FY.
There we go. There we go. All right. So the gross section yielding capacity is 0.9 FY AG. And so do we have all those values? Looks like we do, don't we? I mean, we've got the FY, which is 50 KSI. We've got the AG, which is 7.08. So 0.9 times 50 KSI times 7.08 inches squared. What are we getting here? Anybody have an answer for me?
Well, if I did my math right, well, Trevor got it right, 318.6.
Is that what you got?
Yep.
All right, so therefore, phi PN is 318.6 kips. Okay, so what I'm going to do is I'm going to sort of box that. I'm going to box it in blue. And I'm going to say gross section yielding. Okay, so what that means is if I, here's a tension member. I'm yanking on it. I am pulling on it in tension. And I am saying that according to the limit state of gross section yielding, I have a usable strength of 318.6 kips. That's what that says. So under that limit state, that is the maximum amount of factored load I can put on that section before I violate safety conditions under that limit state. That's not the only limit state. We've got a whole nother one we've got to consider, but we're going to do that here in a second. Everybody with me so far? Don't worry, we'll come back to this number here in a bit.
Would that be considered like the yield stress for like the stress strain curve, or is that like ultimate stress?
That's basically the yield stress, but what we're doing is saying, a W8 by 24, if we're limiting a W8 by 24 to 50 KSI, how much load would it take to get there? And then taking that load and backing it down by 0.9 for a safety factor for uncertainty's sake. Does that make sense?
Yeah, it does. Thank you.
So after that load, it will experience permanent deformations. But keep in mind, we've also reduced it a little bit. We've multiplied it by 0.9. So that's answering what Mr. Roman said. All right. Everybody, did I answer your question? Everybody with me so far? Okay. Now, let's talk about the net section fracture. If we understand what the expression is for gross section yielding, what's the expression for net section fracture? So it was 0.9 FYAG for gross section yielding. What about net section fracture? .75. Now, you almost got it. You missed one, but you're on the way there. You have 0.75 times the net area times our shear lag factor, but you missed one. There's the FU value, the tensile stress. Yeah, exactly. So 0.75 FU AE, and AE is just the net area times U. So let's look at our section. We know the FU value, right? It's A992 steel, so we know that the FU value is 65 KSI. So we know the 0.75, we know the 65 KSI, but what we don't have is the net area, and we don't have the shear lag factor. So let's take care of each of those one at a time. Now, let's talk about net area, okay? So let's do net area first. So the net area is going to be the 16.1-31. Hold on. That's the okay, all right, I see what you're talking about, Zach. You're asking something a little different. Those expressions on 16.1-31 are for built up members, so that doesn't really apply for what we're talking about here. We're just talking about a regular old rolled shape. Now, we are going to use the expressions on 16.1-30 because we're going to have to compute our shear lag factor here in a second. Yeah, the ones we're talking about, the formulas, we're talking about the stuff on 16.1-28. Those are the FU times AE, and then AE is the net area times U. Everybody with me so far? Okay. All right. So first thing we need to compute is the net area. Now let's look at this section for a bit. And let me ask you a question. We don't have any stagger factors. Like there's no staggered connections here. All this is just a roll shape going like this. And there's just, bolt holes like that. And that's all we've got. So no stagger factors or anything like that. So it's just going to be the gross area minus some amount of bolt holes. How many bolt holes do you think we're going to subtract for this section? 4, right? Because, it's literally right here, right? That's really all we need. That's a cross-sectional view, and we're subtracting 4 bolt holes. So what's the formula? We take the gross area minus 4, and we know the diameter, we know the area of a hole is the diameter times the thickness. And what thickness are we going to use? The thickness of the flanges, because look, the bolts are going through the flange, right? So it's the diameter times the thickness of the flange. So that's the 7.08 minus 4 times, and that's 7/8 of an inch times 0.4. And so what does that end up equaling? 5.68. Do I have a second on that? All right. So everybody with me so far? So we're just basically taking all the stuff that we've been working on for the past few lectures and just putting it all together. All right. Now, we got to do the shear lag factor. Okay, that's our U value. Okay, we got to figure that out. Okay, so I want to scroll up a bit. I want to go back to my section. Okay, first off, this one's going to be weird because this is a W section connected via the flanges. So the way that we compute our X bar is going to be a little different. So just bear with me on that. But what I want everybody to do is I want everybody to turn to 16.1-30. So this is table D3.1. Here, I'll write it out. On page 16.1-30. And what I want everybody to do is I want you to look at that table, and I want you to tell me which cases are we going to have to consider. I'll help you out. We are going to have to consider case 2. Okay? We don't look at case 1. Remember, case 1 and case 2 are sort of our baselines. And case 1 is where all of the cross-section components are connected, and case 2 is where only some of them are connected. And we don't have all the components are connected on this problem because there's no bolts going through the web. It's only going through the flanges. So case 2 would apply. Are there any others that apply?
Can you scroll back up to the our plate we're looking at?
Sure.
Well, we could consider case 7.
Case 7.
And we can also say it's case B in this case, well, the second one, because we have 4 more fasteners according to the image.
But that's through the web.
Oh wait, flange.
See, yeah. So that you're bringing up indirectly a really good point. Make sure that you read the verbiage on the cases, because it says with 4 or more or fasteners, but that's with the web. This is through the flange. But you are correct that we are going to have to consider case 7. All right. And does everybody see that it's not only case 2, but it's also case 7? Does everybody see that?
What about case 4? Because no, even though it's a W shape, it's with connected elements.
Well, case 4 involves welding.
Okay.
And as Mr. Riggs said, case 8 would be if we were dealing with an angle. So case 8 would be, like an L shape. And so since we're dealing with an I shape, like a W section, it wouldn't really apply. All right. So let's take each case one at a time. Okay. Let's start off with with case 2. So in order to handle case 2, we need the connection length and we need the connection eccentricity. Let's start off with the connection length. Somebody tell me how long the connection is. What is L, like our L connection, going to be? It's 9 inches. It's not 11, it's 9. Remember, we only consider the center to center spacing on the bolts along the direction of loading. So case 2. LCON is 9 inches. Okay. Now, the X bar, this is the one that's new. This is the one that's a little weird. Okay. So whenever you have a W section that is connected via the flanges, and it's only for this case. So you only have to remember this for this case. What we do is we convert that into an equivalent WT. Okay. All right. We convert that into an equivalent WT. So if we have a W8 by 24, an equivalent WT would be one that is half as deep and half as heavy. Okay. So the X bar, what we do is we look up the property, the associated property for a WT 4 by 12, and what we're interested in is the distance from the connected face to the centroid. That's what we're interested in. And for a WT shape, that's actually Y bar. So in this specific instance, you look up the Y bar for a WT 4 by 12. So what is the Y bar for a WT 4 by 12? And I'll tell you, you're going to be in table 1-8. Okay, so 0.695 inches. Okay, so we've got X bar, we've got L, therefore our U for case 2 is 1 minus X bar over L. So 1 minus 0.695 inches over 9 inches. And so what is that? .923. Okay, and we got a second. I said it uses the Y bar. So you're looking at the so if you go to table 1-8, if you look how far is it from the top of the section to the centroid, and if you look at that image on the top right or the top left of the page, that's the Y bar dimension. Did that answer your question, Mr. Smirchinsky? Hold on, I got a question. Hold on. Who was that?
It's me.
Yes, yes, sir.
If you had a bolt connect, and I don't know if this would change, but you said this only applies to this specific case. If we had a bolt that was running through the web, would you still use the Y bar?
No, you would not.
So you would go back to the X bar for the W shape?
No, this is, so if that was the case, and this is a little bit rare on the tension member side, we don't do this very often, but if you had the bolts going this way, like this, what you would do is you would try and come up with an equivalent channel. Like you'd split it half the other way. And so you would look for that distance. It's kind of tough because it's not like with the WT sections where it's 1-to-1, like you can easily find the property. It's a little tough. And a lot of times what people will do is they'll just go to like K7. And we're going to see K7 here in a second. It's a little funky, I will admit.
Is there ever a time where you have both the bolt holes on the flange and the web? Or no?
Yes, and in
Okay.
in that instance, you would apply case 1, because case 1, all of the cross-sectional components would be connected, and you
Okay.
would just be 1.
Okay. Thank you.
These are great questions. This is the stuff. Yeah, if you ever got questions about this stuff, let me know. All right, everybody good? Okay, let's look at case 7. So first off, case 7 states WMS or HP shapes. So those are basically the I-shaped cross sections or the T's cut from these shapes. So this applies, and it branches off, and there's two different components. So with the flange connected with 3 or more fasteners in the per direction or per line in the direction of loading, or with the web. So we don't need to worry about the one with the web. So let's read that again. With the flange connected with 3 or more fasteners per line in the direction of loading. Does that apply to our connection? How many fasteners do we have per line in the direction of loading? And keep in mind, you know, we're yanking on it like this. 4, right? So this applies. Now, if for some reason this had 2 per line, we just would not use case 7. We would just move on and only use case 2. So just because it violates doesn't mean it's bad. We just wouldn't apply it. So we're looking at case 7, and if you notice, we've got to compare some values. We've got to compare BF, and we've got to compare 2/3 of the depth. Okay, so now you can see why I had you look those up earlier, right? So the B sub F was 6.5 inches and 2/3 of 7.93 inches. So what's 2/3 of 7.93? Doesn't need to be exact. What is it, like 4 something? Somebody help me out on that one. Okay, 5.28. Okay, so 5.28. So if I were to compare BF and 2/3 of the depth, I think it's fair to say that that's greater. And if that's the case, what's U7? .9. Now, of these two, so I've got, I've got a value here. I've got, U2 is 0.923, and I've got U7 is 0.9. Which one do I use? And I'll give you a hint. Read case 7 again. Use case 2, because it states if U is calculated per case 2, the larger value is to be used. Again, this is just fitting the test data from the lab better, hence why we use case 2, because think of case 7 as sort of like a lower bound. It's like a check to make sure that U2 doesn't yield any wonky results. So therefore, take U to be 0.923. And so we'll underline that in red just to make sure we're clear on that. Okay. Any questions? I want to make sure this is clear. I don't want this to be funky. Again, these are empirical expressions, so you're just sort of following the spec and making sure that you read and understand the provisions. All right. Everybody good? That's what I like to hear. All right, so now we can go back. We can say, wait a minute, didn't we have that net section fracture expression? And I think it was, if I remember, 0.75 FU, and then it was AE, but AE is just the net area times U, right? And so, well, we know 0.75. We know 65 KSI. I think the net area, if I remember correctly, wasn't it like 5.68? Yep, I'm looking that up in the chat, 5.68. inches squared, and then this is 0.923. So what do you get for VPN here? All right, 255.58. I'll be so one thing I'll mention in terms of specificity, usually I'll say something like 255.6. I usually don't get any more specific than that on my capacities because, we're talking about on a scale of, that's 255,000 pounds, plus or minus 100 pounds really doesn't matter all that much. Do I have a second on that though? Does anybody have can anybody check me on that? All right, that's what I like to see. All right. Boom. Okay. So I've got a couple things I want to do to close out this problem, but we've got a little bit more work to do. So let's sort of look at our capacities. So we got gross section yielding is 318.6 kips. And we got the net section fracture is 255.6. Now, I want to ask a basic question and I want a basic answer. If I were yanking on this thing, what's the capacity? How much can it hold up before I say it's no more? Is it the bigger or the lower? And Mr. Blizzard is saying use the lower. He is right. Okay. If I'm yanking on this thing and I keep increasing the load, which am I going to hit first? I'm going to hit the net section fracture. Okay. So what we say in engineering speak is we say this governs. Okay. So what is VPN? VPN is 255.6 kips. All right. So you could sort of think of that as like an answer, but that's not the entire story. Okay. We have to, all of that is the resistance side. Now I want to look at the load side and I want to look at the factored loads. Now, if you remember, this section was subjected to a dead load of 80 kips and a live load of 90 kips. This is how much we're actually placing on the section. So it'll be one of the first two cases. Yeah, so we have 1.4 dead. So if you remember, case 1 was 1.4 dead. Case 2 was 1.2 dead plus 1.6 live. I don't know about you, but by observation, I could just look at this and see that case 2 is going to yield a bigger answer. So I'm just going to use case 2. And so case 2 says PU is 1.2 P dead plus 1.6 P live. And so what are we getting for PU? 240 kips. Do I have a second on that? Yeah. All right. Now, what I want somebody in this chat to do is I want you to look at these two numbers. What does that mean? I want to know what this means. So we have a resistance of 255.6 kips and a load of 240 kips. That's correct. It's safe. Okay. If instead of a PU of 240 kips, if we got 280, the member would not be safe. And what that would mean is that we would have to redesign the member. Instead of using a W8 by 24, we'd have to use something that's bigger because it would need to be beefier to resist the load. Now, before I close the problem out, there is one more thing I want to check, and there's one check that we forgot. I don't know, forgot. It's just something we needed to do near the end, and that's the slenderness check. So if you remember, R min was RY, and I believe that was 1.61. And so the member is 40 feet long. So therefore, L over R is 40 feet over 1.61. I think I forgot something, didn't I? I forgot to multiply it by 12. There you go, right? Got to convert those feet to inches. So 40 times 12 over 1.61, what is that? So 298.14, so L over R is 298.1. And so we meet our slenderness limits barely. So meets slenderness limits. This is a full-blown tension member analysis problem from start to finish. We've taken a member, it had load on it, we factored that load, we compared that against its resistance, we computed that resistance according to two different limit states, and we found that the member has sufficient strength to adequately and safely resist that load. We also checked the service limit state looking at slenderness. Whew. What do you think? Any questions? Pretty much this next one is, the only difference is it's not a rolled shape. Yes and no. And so what I mean by that is, if you look at the homework assignment, and let me pull it up here. Okay, so what this homework assignment is, it's going to be very similar to this process. What's going to be different is, number one, it's a channel. It's not a rolled shape or a wide flange. So because it's not a wide flange, you don't have to consider that case 7 or whatnot. You really only have to consider case 2. And we did an example in class on how to compute U for that. So that's easy. The only thing that makes the homework a little more challenging is that the connection has stagger. So when you compute the net area, you're going to have to consider stagger. But other than that, the process is very similar. And I want you to check whether or not it meets gross section yielding, net section fracture. And then I want you to see whether or not it meets the slenderness check. But basically, yeah. And then Friday, I think we're probably going to do another similar problem where we, I don't want to say ramp it up, but we add, a couple little things to it. Yeah, I mean, that's sort of the point. And here's the thing, if you understand analysis, design is just this a little bit in reverse. We make some assumptions, we pick a member, and then we check that member. And that's design. Now that's design for tension members. For beams and columns, we've got some tips and tricks and some tools in the manual that make it a little easier for us. But that's for another day. Well, okay, a couple things. Be careful using that word beam. Beam implies bending. We're not bending it, we're yanking on it. So make sure you're using the right terminology. This is a tension member, we're just yanking on it in tension. Now, how would it apply to multiple members at once? Well, I don't want to say it really wouldn't. Now, if you have a building and you have multiple members that all have the same geometry and all have the same loads, then what you can do is design one of those members and just use it over and over again. Now, of course, that changes depending upon if you have a structure and the members have different geometry or different loads, then you're going to have to do each one separately. But I don't know any other way to answer that question. Or did I answer it? Okay. All right, any other questions? Yeah, this is when I think steel design starts to get a little fun, because now it's real. Now you can see sort of the big picture. All right, everybody, I'm going to go ahead and call it. On Friday, we'll probably do another example, but I'm going to make it a little funkier just to, give you some more practice. And then next week, we're going to do some design. That's all I have, everybody. I will see you all. You all have a wonderful rest of your week. We'll see you on Friday.